All right, today we're going to unlock the math behind some of the most powerful forces out there. We're talking everything from explosive population growth to the super slow decay of radioactive elements. We're going to build a toolkit for solving equations that, can look pretty intimidating, but are absolutely key to understanding and predicting the world around us.
So our story actually starts in a pretty strange place, Australia, back in 1859. There was this landowner, Thomas Austin, who thought it would be a bit of fun to have some rabbits on his property to hunt. A little bit of sport,
He released just 24 rabbits. That's it. But see, Australia had plenty of food and almost no natural predators for them. So that tiny little population, it just exploded. We're talking millions of rabbits in less than 10 years. It got so bad, they called it the rabbit plague.
Now, this isn't just some wild story. It's a perfect real-world example of exponential growth. And it gets you thinking, right? How can we use math to model something that grows that fast? How do we predict it, or even try to manage it? Well, answering that means we need to get comfortable with two specific types of equations.
The key is solving two kinds of mathematical puzzles. On one side, you have exponential equations. This is where your unknown, the x, is kind of trapped up there in the exponent. And on the other side, you've got their inverse, logarithmic equations, where the unknown is inside the logarithm itself. They might look totally different, but they're really just two sides of the very same coin. So let's dive in and build our first toolkit. This one is all about taming those exponential equations, and we've got a couple of really cool tools we can use. Our first tool is the common base method, and it's actually pretty elegant. It all comes down to a really simple but super powerful idea called the one-to-one property. It just says that if you have two expressions with the exact same base that are equal to each other, well then their exponents have to be equal too. It's like getting both sides of the equation to speak the same language. And check this out, it's a perfect example. We've got 3 to the power of 2x minus 5 equals 27. They look different, right? But wait a second, what is 27? It's just 3 times 3 times 3. It's 3 cubed. So once we rewrite 27 as 3 to the power of 3, hey, look at that. Both sides have a base of 3. Now we can just set the exponents equal to each other. 2x minus 5 equals 3. A little bit of quick algebra and boom, x equals 4. Easy.
Okay, that's awesome, when it works. But what happens when you get something like 5 to the power of x equals 18? I mean, you can't just write 18 as a power of 5. So, are we stuck? No way. We just need to pull out a bigger tool.
And for these tougher problems, we bring out what I love to call the logarithm hammer. Logarithms are the secret weapon here because they're the inverse of exponents. They have these special properties that let us basically crack the equation open and pull that variable right down from its perch in the exponent.
So here's the game plan. Step 1, get the exponential part of the equation all by itself on one side. Step 2, take the log of both sides. And honestly, it doesn't matter if it's the common log, the natural log, as long as you do the same thing to both sides. Step 3, and this is the magic part, you use the power property of logs to bring that whole exponent down in front. And just like that, your variable is free, and you can solve the rest like any normal equation. Okay, so we've handled the exponential beast. Now, let's switch gears and put together our second toolkit, this time for unlocking logarithmic equations.
Our first tool here is something I call the exponential flip. It's a neat trick that uses the very definition of a logarithm to kind of turn the problem inside out. See, a statement like log base a of x equals y is really just a fancy way of saying a raised to the power of y gives you x. So by rewriting it, you can change a weird-looking log problem into a much more familiar exponential one. Let's take a look at this one. Log base 2 of the quantity 3x minus 5 equals 4. Let's do the flip. The base is 2, the exponent is 4, and it all equals the argument, 3x minus 5. So that's just 2 to the 4th power equals 3x minus 5. Well, 2 to the 4th is 16, so now we just have 16 equals 3x minus 5, and hey, that's an easy one to solve, and we get x equals 7. And you guessed it, just like their exponential cousins, logarithms have their own one-to-one property. It's super intuitive. If you have a log with the same base on both sides of the equal sign, you can basically just drop the logs and set the stuff inside the arguments equal to each other. It's a perfect match.
Okay, so this all seems pretty straightforward, right? But hold on. With logarithms, there's a hidden trap you really have to watch out for. Just because you did all the algebra perfectly doesn't mean your answer is actually a real solution.
And this is where we have to talk about something called extraneous solutions.
The best way to think about an extraneous solution is like a ghost. It shows up when you're doing all the math, the algebra checks out perfectly, but when you try to plug it back into the original equation, it just vanishes. Why? Because it breaks one of the fundamental rules of the game.
And here it is. This is the golden rule of logarithms. You absolutely have to remember this. You can never, ever take the log of a negative number or zero. The thing inside the log, the argument, has to be positive, always. So the bottom line is, after you solve any log equation, you must plug your answer back in to make sure it doesn't break this rule. If it does, that answer's no good. It's extraneous, and you have to toss it out.
So, we've built our toolkits, we've got our strategies. But why does any of this really matter? I mean, we started with a story about rabbits, but these equations describe so much more. They're the hidden language of compound interest, of population growth, of radioactive decay, even the way we measure sound in earthquakes.
I mean, just think about radioactive decay. The half-life of a substance, that's the time it takes for half of it to decay away. The time scales here are just mind-blowing. For a medical isotope like gallium-67, it's just 80 hours. For carbon-14, what we use for dating ancient artifacts, it's over 5,000 years. And for something like uranium-235, we're talking over 700 million years. You can't predict that stuff without these equations.
So with the exact same tools we just learned, isolating the exponential, using that logarithm hammer, we can start asking and answering some really specific questions. Like, say, how long would it take for just 10% of a chunk of uranium-235 to decay?
And the answer, it's just staggering. It would take about 107 million years. That's a number that's so big, it's almost impossible to really wrap your head around. But we can calculate it with confidence, all thanks to these methods.
And that really brings us full circle, doesn't it? As the source material from OpenStax puts it so well, whether we're talking about rabbits or atoms, these functions and the equations that come from them are how we analyze our world and make incredibly important predictions about what's going to happen next.
So at the end of the day, these equations aren't just abstract problems in a math book. They are the hidden operating system for growth and decay all around us, all the time. Which kind of leaves us with one last question to chew on. What other parts of your world, from the money growing in your bank account to the music reaching your ears, are secretly being run by these very same powerful equations?